So the heat rays are free to escape to space. And what determines the amount of heat the Earth loses is the temperature at this height. An increased greenhouse effect takes place when there are more gases in the atmosphere that trap or absorb the heat rays, so that the height where the planet loses heat increases, or it happens at a higher height. The way that affects the temperature at the surface depends on this temperature profile, which is determined, for instance, by the gases, for instance, the humidity. And I will get back to this vertical temperature profile later on, so please keep that in mind. What determines the heat loss at the top of the atmosphere is based on the Planck's laws. Planck's laws describe the relationship between light intensity and its colors and the temperature. Light is pure energy. This y-axis here indicates the intensity of light, and the x-axis here marks the color determined by the wavelength. These different curves are calculated for objects with different colors. The yellow curve represents the light from the sun with a surface of 6,000 degrees Kelvin. That makes it look yellow. Of course, the Earth's temperature is much lower, so that the Earth, according to Planck's law, emits radiation at infrared range. It's light that we cannot see, and that's light which I refer to as heat rays. But the laws of physics also tell us something else. It tells us that the planet loses heat at the same rate as they receive energy from the sun. So the heat loss is determined by the temperature as well as the distance away from the sun, because the sunlight gets more and more diffuse. So we can make simple calculations of the temperatures based on the sun's intensity and the distance from the sun. In these simple calculations, we neglect the greenhouse effect. So this figure here shows a comparison between the calculated temperatures and the measured temperatures. And the perfect results will lie on the diagonal. My calculations fit with the observations quite well, but there's one planet that doesn't fit the picture. That's Venus. Venus has a much higher temperature than my calculations estimate. And Venus is about twice as far from the sun as Mercury, and yet it has a warmer surface. Venus has a thick atmosphere made almost entirely of CO2. And Venus is also a very bright planet. You can often see it in the night sky, because 75% of the sunlight is reflected away before it penetrates the atmosphere. I guess since I was given a label climate alarmist, I have to talk about Venus. And Venus is the extreme case. It's, I think there's hardly any risk that, such a greenhouse effect on Venus will happen here on Earth. Although when it was discovered that Venus had such high surface temperatures, there were some concerns about a runaway greenhouse effect. But I think we can exclude that. But nevertheless, Venus tells us that the greenhouse effect can be quite potent, and that the atmospheres are not that easily saturated. But what about the greenhouse effect on Earth? How much does the greenhouse effect matter for us? So let's have a look at the climate of the past and see what that can teach us. This figure shows the temperature and ice and greenhouse gases over the last 600,000 years. You can see evidence of ice ages and warm spells. And these are marked with different bands, like the greys show the warm periods here. So what do we see? The climate has changed. We see that the climate is sensitive, or the temperatures are sensitive to changing conditions. The climate is sensitive to forcings. And one explanation for these ice ages, or what triggers it, is that the Earth changes in the Earth's orbit around the Sun. But that is estimated to be quite weak. So something else has to reinforce the effect. And we think, and when we see this high sensitivity, that suggests to us that there are some reinforcing or amplifying feedback mechanisms in climate. And that would also explain why you see natural variations which do not need to be forced. The climate is changing all the time. What we see from here is that the amplification mechanisms most likely involve greenhouse gases because they seem to march in step with the temperature, albeit the CO2 lags temperature by a small increment. What does that tell us? It tells us there's a mutual dependency between the temperature and the greenhouse gases. And what happens is that the greenhouse gases and the temperatures, they affect each other, so they drive each other up higher during a warming phase. Well, let's look at more recent times. This figure here shows estimates of the global mean temperature. The red curve represents the temperatures collected by the Hadley Centre in the UK and the climate research units, which has been discussed in the blogosphere. The black curve represents the corresponding temperatures from NASA GISS. But you also see some estimates derived from what we call reanalysis. And reanalysis are the best picture we can get of the state of the atmosphere because they are generated by weather models fed with all available observations. Surface temperature measurements, radio sounds, satellite data. You get data from the flights. Every time Fred flies over here, they collect flights and feed them to the weather models and ships. So what do we see? For one thing, the NCEP reanalysis, that's American reanalysis, and the NASA GISS temperatures suggest that the 2005 was the warmest on record. The other data suggests that 1998 was warmest due to the strong El Niño that year. But all these show similar feature, they only differ in details. And they all show increasing trends. The same thing you will see if you look at sea surface temperatures. If you look at the sea level heights, you will see consistent trends in ice and snow and biological phenomena. You'll see changes in the atmospheric circulations, and you'll see changes in the rainfall patterns. But maybe this is natural. Maybe this is just happens by itself, spontaneous. Well, we can look back in time and see if we can learn something more. This figure is taken from the most recent IPCC. It shows estimates of the northern hemispheric average temperature. And these we call reconstructions because they are derived from tree rings and sediment cores, and they're not temperature thermometer readings, they are estimated. You'll also